In this video, we'll learn about the matrix inverse. How do you undo multiplication? Let's start with an example. Let's start by multiplication by numbers. For example, suppose we wanted to undo multiplication by 7. So if you multiplied something by 7, in order to undo that operation, you need to next divide by 7, or equivalently multiply by 1 over 7. So the number 1 over 7 is called the multiplicative inverse of 7. In general, the multiplicative inverse of a number a is the number 1 over a, and it satisfies that a times a inverse is equal to a inverse times a is equal to 1. Can we do something similar for matrices? Well, there are some immediate concerns. First of all, matrix multiplication is not commutative. And so, while for numbers, a times a inverse and a inverse times a, we know those are the same things because multiplication of numbers is commutative, for matrices, those are two different things. And so we need to really require both. If we need to consider both a times a inverse and a inverse times a, then it turns out a needs to be a square matrix. Finally, what's the appropriate replacement for this number 1 here on the right-hand side? We'll look into that first. Recall that the n by n diagonal matrix, all of whose diagonal entries are 1, is called an identity matrix. So for example, right here we have a matrix of size 2 by 2, and the diagonal elements are 1. We call that matrix I2. The next matrix is a 3 by 3 matrix, and it has 1s all the way along the diagonal zeros. Otherwise, it's called I3, and similarly for I4. Why is the identity matrix so special? It turns out the identity matrix is the neutral element of matrix multiplication. This means if A is an n by n matrix, then I can multiply A by this identity matrix, either from the left or from the right, and I retain A after this multiplication. So in some sense, the identity matrix acts like the number 1 acts in multiplication of regular numbers, because any number multiplied by 1 is also equal to the number that we began with. So therefore, for the matrix inverse, we need to look to find a matrix such that the product of the matrix and the inverse equals the identity matrix. So let's look at an example. Consider these two matrices A and B that are given right here. What is A times B? We multiplied two matrices by taking the first row of A and multiplying it with the first column of B. So 3 times 5, that's 15. Plus 2 times negative 7, so that's 14. And then for the element next to it, we take the first row of A and the second column of B. So 3 times negative 2 is negative 6. 2 times 3 is plus 6, and so forth. When I do this out, I end up with the identity matrix I2. Similarly, I can verify that B times A, so now I wrote down B first and then A. If I multiply those two matrices, I also get the identity matrix. So it looks like this matrix B is a really good candidate to be called an inverse of A, because if I multiply A from the right or from the left by B, I get the identity matrix. Now, could there be another matrix C that's not equal to B that also has this property that A times C and C times A both equal the identity matrix? Well, in that case, I could write B as B times the identity matrix. And instead of writing the identity matrix right here, I replace that with A times C, because A had this property that A times C equals the identity matrix. But now, multiplication of matrices is associative, so I can move the parentheses from here to over here. So I can perform the product B times A first and then multiply the result by C. But what is B times A? B times A is the identity matrix. So this equals the identity matrix times C. That is simply C. And so we see that B must be equal to C. In other words, the inverse of a matrix, when it exists, is actually unique. So B is the unique matrix that satisfies that A times B and B times A equal the identity matrix, and therefore we call B the inverse of A. Or in symbols, we say B is equal to A inverse. Let's look at another example. Suppose A is the matrix 1, 1, 2, 2. Can we find a 2 by 2 matrix B, again, such that A times B and B times A both equal the identity matrix? What is A times B? A times B equals 1 times A plus 1 times C. And for the next entry, I get B plus D Then I have 2a plus 2c here, and 2b plus 2d over here. And we need that to equal the identity matrix. So what can we conclude from here? We can conclude that a plus c must equal to 1. Furthermore, b plus d must equal to 0. Furthermore, 2a plus 2c must equal to 0. And finally, 2b plus 2d must equal to 1. So those are the equations that I just showed you. But that's a contradiction, because how can a plus c be equal to 1 and at the same time 2a plus 2c to be equal to 0? 2a plus 2c is simply 2 times a plus c. But if a plus c was equal to 1, then 2a plus 2c is equal to 2, and 2 is not equal to 0. So there's a contradiction, and then we also get a similar contradiction with these two equations right here. In other words, I cannot find a matrix B such that A times B is equal to the identity matrix. And so therefore, this matrix A does not have an inverse. So we've seen one example of a matrix that did have an inverse, and another example of a matrix that does not have an inverse. We say A is not invertible. We're now ready for a definition. For an n by n matrix A, we say that A is invertible if there exists another n by n matrix B, such that A times B and B times A both equal the identity matrix. If A is indeed invertible, then the matrix B is unique and is called the inverse of A and denoted A to the negative 1. And therefore, A times A inverse is equal to A inverse times A is equal to the identity matrix. So now that we've seen a definition of the inverse of a matrix, we're ready for some examples.